yesterday we did the web quest, right? And so we were supposed to kind of start to get an idea of what the almost 4 laws were. So today we're going to go back and we're going to revisit each law. And I'm going to show you the equation and I'm going to show you how to solve for them. Okay, so first of all, the first law we talked about yesterday was Boyle's law. Boyle's law incorporates 2 variables. It incorporates pressure and volume. However, in this law, the temperature has to remain constant, which means it doesn't change. So this we're going to do in the first box. When we get to the second law, we're going to do it in the second box of your 4 square, the third law in the third box, the fourth law in the fourth box. Okay. The temperature is constant, which means that our pressure and our volume are inversely related. So when something is inversely related, it means as one increases, the other one is decreasing. So if our volume is increasing, and the pressure should be decreasing. So if this room starts getting bigger, we're going to have more and more and more room to spread out and run around, right? If our room is getting smaller, we're going to have less and less and less space, so the pressure is probably going to start increasing because we're going to start getting closer and closer and closer to each other. So we get an equation of PV equals PV. Now, where have we seen that before? We've seen one very similar to that. When we were dealing with molarity, we learned the equation MV equals MB. So it looks very, very similar. This one deals with molarity. This one deals with pressure. Okay. But this right here is very important, and this is the part that is often overlooked. Okay, these 3 laws, something is always held constant. This one deals with pressure and volume. Temperature is held constant. So for the next 4 laws, we're going to be dealing with these same 3 variables over and over again.
So we're putting on this square.
Well, we're going to do an example here in just a second. No, well, tomorrow maybe. All right, so let's do an example. Now, on the test is the part where everyone likes to fight me on showing my work. Now, do I expect you to show me every single step? No. Do I expect you to do some of the steps in your head or in your calculator? Yes. But since we're going to actually learn 5 different equations, so at the very least, I expect to see an equation, some work, and an answer with a unit. I expect to see 3 steps in some way, shape, or form, okay? So, this one is going to be using the equation we just talked about, PV equals PV. Now, some people like to list their variables along the side. If you're not very good at math or if that really helps you organize your thoughts, then you're more than welcome to do that. But I always put my initial on the left and my final on my right. So, a balloon contains 30 liters of helium gas and 103 kPa. What is the volume of helium when the balloon rises to an altitude where the pressure is only 25 kPa? So first of all, does anybody remember what kPa means? It's a unit for pressure. What is it? Kilopascals. So Pascal is our unit and kilo is the metric prefix, right? Okay, so now I'm just going to plug things in. So initially, we are at 103 kPa and 30 liters. It is asking me what my final volume is going to be if my pressure changes to 25. Now, this is inversely related, right? What happened to my pressure? Did it get bigger or get smaller? Smaller. So what should happen to my volume? It should get bigger. So how do I get volume all by itself? Divide by 25. So in my calculator, I'm going to do 103 times 30, divide it by 25, and I'm going to get 124 liters. Now, I'm pretty sure in your calculator, when you put this in your calculator, you're going to get an answer of 123.6. But 30 has 3 sig figs. 103 has 3 sig figs. 25 has 3 sig figs. So therefore, we had to round it with 3 significant figures. So that gives us 124. Not too bad. Easy math, right? Nothing like stoichiometry. All right, what's the second law? Does anybody remember the name of this one? What's the name of this law? Charles' law. Okay, Charles' law deals with temperature and volume. He says that the volume of a fixed mass of gas, so basically if we take gas and we don't add any and we don't take anything away, the volume is going to be directly proportional to the Kelvin temperature. Now, why in the world did I underline Kelvin right there? Because I'm telling you that it has to be in kelvins. Most of the time, we're going to be given degrees in Celsius. And so we then have to convert it to Kelvin. How do we convert to Kelvin? You add 273 degrees Celsius, right? Okay, so these two things are directly proportional, volume and temperature. So that means as my temperature increases, what should also happen to my volume? It should increase. If my volume decreases, what happens to my temperature? Decreases. These two things are directly proportional because as I heat up my temperature, as I heat up my gases, they start moving around faster and it causes them to spread out even farther apart. If I cool down my gases, they're going to start moving slower, which is going to cause them to become closer and closer to each other. Now, sometimes when you're dealing with gas problems, you can get away with not converting to Kelvin because sometimes it's not necessary, but sometimes it is necessary, especially when you're dealing with negative numbers, especially when you're using the equation we're going to learn tomorrow. And so we're just going to always convert to Kelvin, and that way we don't forget to do it. All right, are you ready for our example? Okay. So, a balloon is inflated in a room at 24 degrees Celsius and has a volume of 4 liters. The balloon is then heated to a temperature of 58 degrees Celsius. What is the new volume if the pressure remains constant? Now, for whatever reason, I can't get that to go away. So, there's the answer, but we're going to figure out how to get to the answer. So, I'm going to use the equation we just talked about. We're going to take our volume divided by our temperature equals our volume divided by our temperature. Our original volume was 4 liters. Our original temperature was 24, but we don't want Celsius, so we're going to go ahead and add 273. Our final volume is what it's asking us to solve for, and our final temperature was 58, but again, we don't want Celsius, so we're going to go ahead and convert to Kelvin. And this would be one of those examples where we don't necessarily have to convert to Kelvin, but we're just going to always do it so we don't forget to do it. Okay, so what happened to our pressure? Did it increase or decrease? Increased. So what should happen to our volume? Increases. So we're just going to go ahead and we're going to see if we were right or not. So I'm going to simplify. So we're going to have 4 over 298 equals volume over 331. How do I get volume all by itself? Oh, 297. Sorry. The next one's 25 degrees. So I need to multiply by my 331 to get it on the left side. So basically, to get my volume all by itself, I'm going to take 331 times it by 4, divided by 297, and I'm going to get 4.4579. Does anybody remember how many sig figs we were allowed to keep? The problem's not up there anymore, so it's hard for us to see, but they gave us 24 and 58 degrees Celsius. So we are only allowed 2. So how do I round this to 2? 4.5. And what's my unit? Liters. Okay, who remembers the third law's name?
That's the
Gay-Lussac's, which is always fun for us to say. But Gay-Lussac's law, this one deals with, weird. Sorry, it's being difficult. There it goes. This one deals with pressure and temperature. This one says that when the volume is constant, the Kelvin temperature is directly proportional to the pressure. So what that means is as our pressure is increasing, so should our temperature. If our temperature is decreasing, so should our pressure. And so we get an equation that looks very similar to Charles' law, except we're not dealing with volume, we're dealing with pressure. Okay, so this problem says the gas in a used aerosol can is at a pressure of 103 kPa at 25 degrees Celsius. Just to kind of give you some perspective, sea level's pressure is 101.3 kPa, so we're pretty close to sea level, right? And 25 degrees Celsius is room temperature. And so this is kind of an average. This is like if you went and grabbed a can of hairspray off the counter in your bathroom. This would be the kind of pressure it's under. If you take it and then throw it into the fire, our temperature is going to increase to 928 degrees Celsius, which is a really, really big raise in temperature, right? So we are going to use that equation we just saw. We're going to do pressure over temperature equals pressure over temperature. So our initial pressure was 103. Our initial temperature was 25, but we need it in Kelvin. So we're going to get 298. That's going to equal our new pressure, but again, we have to convert it to Kelvin. Which gives us, how do I get my pressure all by itself? We got to get 1201 on the other side. So my new pressure is going to be 415.11. Now if we look back at the problem, how many sig figs do I get to keep? 2. So how do I round 415.11 to 2 sig figs? 420. And what's my unit? Kilopascals. And I know that it's getting harder to see because there's that little hand right there. The smallest. Okay, but these three gas laws all had something constant, correct? Is being at a constant temperature realistic? No, because think about today, our temperature outside is going to fluctuate 50 degrees today easily. Is being under constant pressure realistic? No, because pressure can change if a storm system rolls in, right? Is being under a specific volume realistic? No, because volume changes when temperature and pressure change. If we can't control temperature and pressure, we're not going to be able to control our volume. And so these are not always something that we can control. So sometimes all three of them change, and that leads us to the combined gas law, which is exactly what it says. They take the three gas laws and they combine them all together. So if we look at our three gas laws, we had PV equals PV. We had V over T equals V over T. And we had P over T equals P over T. Now, does anybody see any similarities here? What do we see about pressure and pressure? They are always on top, right? What do we notice about our temperature is always on the bottom. What about our volume? Our volume is always on the top. Do you guys see that? So basically what they did is they took these three things and they put them all into one thing. Pressure was always on the top, so they left it on the top. Volume was always on the top, so they left it on the top. Temperature was always on the bottom, so they left it on the bottom. And they just combined all three of them into one fell swoop. We get a new equation. But do you guys see how it looks just like the last equations we were doing? Okay, now the question I always have from students is, how do I know when I'm supposed to use Boyle's law, and how am I supposed to know when I'm supposed to use the combined gas law? Well, the question is, how many variables are you given? If they give you 3 variables, then you're going to use combined. If they only give you 2 different variables, then you're going to use one of the other laws. This one you have to use when you're given all 3 variables, and all 3 of them are changing. All right, we ready for the hardest example of today? Yes. Okay. So this one says the volume of a gas-filled balloon is 30 liters at 313 Kelvin and 153 kPa. What would the volume be at STP? Now, on your quiz day, we saw that STP was what? Standard temperature and pressure. Okay, so the question is, what is our standard temperature? Oh. What is our standard temperature? Nope. 0. 0 degrees Celsius. Does anybody remember our standard pressure from Friday? 1 atmosphere. And these are our standard conditions at sea level. Okay, 0 degrees is it's freezing, right? 1 atmosphere is like a normal pressure. Well, if we look at this problem, they give us liters, Kelvin, and 153 kPa. So we need the same units, right? So what is our temperature in Kelvin going to be? 273. Does anybody remember the conversion from atmospheres to kPa? I don't expect you to, but does anybody remember it? Okay. It's 101.3. 1 atmosphere is the same as 101.3 kPa, just like 3 feet is the same as 1 yard. Say it's just a conversion factor. Okay, so now we have our initial conditions, and we are going to change the pressure and the temperature to these conditions. So we're just going to plug it into our equation. Our initial pressure was 153. Our initial volume was 30. And our initial temperature was 313. Our final pressure, we want to lower it, right? Because it started at 123. We're going to lower it to 101.3. It's asking us to solve for volume. And our temperature is also going to be lowered to 273. So now all it is algebra, correct? So honestly, what I'm going to do is I'm going to start simplifying because there's a lot of numbers right here, correct? So I'm going to simplify the left and right side. So 153 times 30 divided by 313 gives me 14.665. And that is going to equal 0.371 times my volume. Now how do I get my volume all by itself? Divide by my 0.371. Oh. And I'm going to get 39.52, wow, 8. How many sig figs do I get to keep?
3.
3. So what do I round this to?
3.5.
39.5. What's my unit going to be? Liters. Okay, so none of this math is incredibly hard. It's just knowing what equation to use where. But did you guys see how all the equations kind of go together? If you know the combined gas law, you know all 4 of them, don't you? All right, so we're going to do some practice today and see how we do.